Good morning, everybody. No, I better not do that. It's my goodbye thing. Good morning, everybody. Welcome to a cloudy, maybe rainy, but wonderful morning at Chem 11:05 with your host, me, Dr. White. Now, important Chem 11:05 announcement. First of all, this Thursday during class, after the lab, I will be giving test number 1. And as it says in Blackboard in the announcement, which you will uh, have gotten an email, test 1 will cover materials chapter 1, 2, and 3, along with appendix A2 and A4. It'll be given in class. It's 100 points, 29 problems. Relax. My tests are designed if you've studied and done the practice problems. You'll be given an hour, but you should be done in about 35, 40 minutes at the latest. And it has 7 multiple choice. Dr. White doesn't like it. Has 8 pages, and the last page, as you've seen, will have important information. That file is already available on Blackboard in lecture, and there'll be a periodic table, the green one, as you've seen, for you to download if you already haven't. And right after the lab, we'll just go right into the lab, and by 10 o'clock or maybe a little earlier, I will send out an email to you with the password for your version of test number 1. Sometime Wednesday afternoon, I will post in the assignment area the 2 versions of test number 1 for you to download. I download both of them, and the periodic table if you don't already have one. And that will be test number 1. Now, a couple important things. First of all, I'll send out an email sometime this afternoon, this evening. Test number 1, like I said, I'll send out the email with the password around 10 o'clock or maybe 9:45. You'll have until 11:30 that Thursday to 1, take the test, and then upload your answers to the assignment area of Blackboard as either a single PDF file, well, I guess it's a single PDF file. And if you don't have a printer, just write out the question number and the answers. You do not, if you don't have a printer, I like that, do not. It's silly Monday. But anyways, you not have to write out the questions, just put down the answers. Now, one word of wisdom to you is before you upload your PDF file for your test answers, check it. Make sure you've got all the questions included in that file. Yes, last semester I had students who didn't. I had to track them down because Dr. White's nice, but please don't make me have to track you down and say you're missing page 8 or 7 of your test. So that's test number 1. Any questions? Also, for test number 1, you should have a scientific calculator. If you don't know how to use a scientific calculator, go back and look at the video, and I'm not sure which date, but it was last Tuesday or Thursday, where I went through how to use a scientific calculator. And if you have any questions, come to my office hours. Now, listen carefully. Because of the Stanley Cup Finals this week, I'm moving my office hours. I think I'm moving them, possibly changing them to help you to another time. But this week, my office hours will be Monday, Wednesday from 5 to 6 p.m. Same login, but this different time frame. Also, I'll send out an email this week. I'm thinking of changing my office hours because they really haven't been helpful to many of you, like most of you this semester. Last semester, it was a good time slot for my students and a lot showed up. But this semester, I know a number of you are working Monday, Wednesday night. So I'll send out an email with a couple of choices of times when I'll have office hours, and I'll ask for you to get back to me. And based on what the students feel are the best times, I'll reset them to those times. All right, another thing, if you're having trouble with Beyond Lab Z in any way, always feel free to come to my office hour or see me after lab for help. Yes, remember, there's no such thing as a dumb question in my class, in my universe. And if you need help, ask. By the way, I make a good lab partner for help. All right, any questions about things coming? Oh, one more thing. I almost forgot. By the way, oy vey and oy vey smear are very popular Yiddish words. But anyways, tomorrow I will be giving my world famous review for the next test. In this case, test number 1. Students have told me that helps them do good on my test, and that's why I'm going to do it. So tomorrow I will be doing test number 1 review. All the labs we're doing in terms of when they're due, the one you did last Thursday is due tomorrow. I don't know, does that answer your question? You're welcome. I'm glad. Remember, always feel free to ask questions, either by chat or whatever. All right. I promised last week, today, I'll be going through chapter 3, problem set. I'll also put out in today, and it's going to be a busy email. I found out I made a mistake. Bad, Dr. White. And instead of going for electron configuration to calcium, I should have kept what I normally do. And you'll only be responsible, highlight that, in coordination. My fingers are, they're working good. But anyways, I said it's silly Monday. I will only ask you to know how to do electron configuration up to magnesium atomic number 12. Shh, that's my gift to you. Shh, don't tell anybody. All right, magnesium atomic number 12, not calcium. All right, let's get going. There's a lot to do, and I've got to get it done today. All right, thumbs up, people. Do you see Chem 1105, Chapter 3? Thank you. Also, for those of you who can, turn on your video. It makes Dr. White, your webcam, makes me happy, which is a good thing. Oh, I see a question. And I believe I set it up for doing labs being done by 4 p.m. Why is that? Because that's when I get done teaching with the other class. Since I'll be busy right after this class, it makes no sense for me not to give you some extra time, because I won't be grading labs because I'll be teaching. All right, this is stuff you should know for test number 1, which is this Thursday. What are the 3 subatomic particles of an atom? Everybody together. You don't have to turn your mic, but say it out loud at home. It's the electron, proton, neutron. The 3 subatomic particles are electron, proton, neutron. You should also know, what is the charge on a proton? And the answer is positive charge. What's the charge on an electron? A negative charge. And finally, well, I don't have it there. What's the charge on a neutron? No charge. The invisible question. Now, how do you determine electrons and protons of an element? You look at the atomic number. If we look at the periodic table, remember the atomic number is the number on this table in the upper right-hand corner. I'm assuming you all know your right from your left. If not, come to my office hours. I'll teach you. But anyways, if we look at carbon, atomic number 6, that means it has 6 electrons, 6 protons. If we look at sulfur, atomic number 16, has 16 electrons, 16 protons. Oh, let's go to the high rent district. Ooh, let's look at gold, AU. Atomic number 79. How many electrons and protons does gold have? Atomic symbol AU, 79. If we go up above, AG is silver and has 47 atomic number, which means it has 47 electrons, 47 protons. And notice I gave you a number here, and this is the atomic number, which is how we get the number of electrons and protons. By the way, this is a sneaky way for me to make sure you know your chemical symbols, that you know lead is Pb, potassium is K, silicon is Si, I already did gold. And remember, the number of electrons, the number of protons in an element is the same as the atomic number. Now, you should know, hint, how to write the electron configuration for various elements up to atomic number 12, that's magnesium. Let me open something I didn't open. All right, thumbs up, people. Everybody see the table, electronic shells and number of electrons in each subshell? Probably not. And the answer is you should. Now do you see it? Thumbs up, people. Help me out. Now do you see it? Yes, you do. Thank you. All right. Zoom told me all this time you were seeing it, and it's not always honest. All right. You should know that electron shells and the number of electrons in each subshell and their names, this is an important information, test number 1. And this will be given to you on the last page. But you also have to know, this I won't, when you go from the top to the bottom, this is the lowest energy shell, this is the highest. Same thing here. You have S is the lowest energy subshell. And F is the highest energy. And you always put the electrons in the lowest shell and the lowest subshell energy-wise of that element until you fill it up, and then you go to the next lowest. So you start with 1, then you go to 2, 3, 4. Remember, 1 has 1 subshell, 2, 2, 3, 3, 4, 4. The subshells S, P, D, and F, any S subshell, remember, a subshell is a number and a letter. A subshell is designated by a number and a letter. So any S subshell has 2 electrons, P 16, D 10, F 14. And notice I give you a little hint about electron configuration. And now, thumbs up, people. Do you see nitrogen on your screen? Oh, you people, thank you. All right, now nitrogen, in order to write the electron configuration, you have to know how many electrons it has. Look at the periodic table. Nitrogen, atomic number 7, 7 electrons. You start with 1s. 1s, you can put maximum of 2 electrons. I did. And one has only one subshell, 1s, and I filled it up. So once I do that, I go to subshell or shell 2, and the first subshell in shell 2 is 2s. Remember, subshell is a number and a letter, and 2s, any s orbital, I can put in 2 electrons. Well, 2 plus 2 is 4. I've got to get to 7. Now, shell 2 has 2 subshells. The first one is 2s. The next one is 2p. And how many electrons can I put in any p orbital? 6, but how many do I have left? 7 minus 4 is 3. I'm done. And here's some more examples. And oh my goodness, I've been talking for all this time and I haven't shared and let you have some fun. Why don't you write the electron configuration for sodium? And I'll help you out. Sodium has a chemical symbol of Na. Let's look at the periodic table. I'll let you figure out how many electrons does sodium have. Time's up. Sodium has 11 electrons, and now I'll let you get back to draw the electron configuration for sodium, and let me help you out. You'll be given this table. And just pretend you're hearing game show music like The Price is Right or Jeopardy or whatever. I haven't watched those programs in decades. Not missing anything either. Remember, you have 11 electrons to fill in the shell and subshells. And the votes are coming in. I just sent out a poll. I'll give you another 20 seconds. I think everybody's done, so I better get to work. How do you do the electron configuration for sodium? Sodium has 11 electrons. The first shell is 1 and the subshell is 1s. In any s orbital, I can put 2 electrons. I do. 1 only has 1 subshell. I filled it. So now I have to go to 2, and the first subshell is 2s. And I can put in 2 electrons. Well, I got 4. I got 7 more to go. 2 has 2 subshells. The first one is 2s. Remember, I'm going down the table. And the next one is 2p. How many electrons can I put in any p orbital? 6. Well, 2 plus 2 plus 6 equals 10, but I have to go to 11, so I have one more. 2 has 2 subshells, and I fill them up. So now I have to go to the next shell, lowest energy, and that's 3. And what's the lowest energy subshell in 3? 3s. Remember, a subshell is a number and a letter. And how many can I put in there? 2, but 11 minus 10 equals 1. So I'm done. And it is 1s2, 2s2, 2p6, 3s1. And that's how you do it. Any questions? All right. And the last question on here is, how many valence electrons do the following elements have? You should know that the valence electrons are the outermost electrons of an atom. Those are the fun ones to play with, because those are the ones you'll learn are involved in chemical reactions. Oh, by the way, tomorrow's lab is, you're going to love it. So how do we find out how many valence electrons, let's say hydrogen have, carbon or oxygen? You look at your periodic table. And for each column, and the first one, even though the alkali metals don't include hydrogen for valence electrons, it is included. And you look at the number on top. And if you don't know your Roman numerals, I put the numeric values in red on this periodic table. And if you look at hydrogen, the number 1, so it has 1 valence electron. And we got to do carbon and oxygen. So carbon, you got to know the chemical symbol and where it is on the periodic table. Here has valence electrons. How many? 4. And if you know your Roman numerals, IV is the Roman number 4. And nitrogen is 5. And oxygen, another one that we were asked, here the number is 6. And if I move myself out of the way, which I just did, let's see if I have any more. Oh, I shouldn't have done that. And I also have on here iodine and krypton. So let's go to our periodic table. And iodine, chemical symbol I, and up above you see number 7. And krypton, remember krypton in our world is a colorless gas at room temperature. It's not a green solid that kills Superman. It's atomic symbol Kr. Look at the top, the number in red, or in Roman numerals 8. So it has 8 valence electrons. And with that, I've covered all the practice problems and material you should know for test number 1, which is coming up this Thursday during class. Be sure to, if you haven't done them, do the practice problems. Now, speaking about having done something, and I'll send this out in today's email. Well, it's going to be a busy email. If you have not uploaded the signature sheet, the assignment area, Blackboard, you get a 0 for test number 1. So make sure today before Thursday, you upload it. Most of you have, but a few of you haven't. So make sure you do it. That file is located both in the syllabus folder and in the assignment area for Blackboard. All right, any questions about anything except the meaning of life? I still haven't figured that out, but anything else? All right, well, in that case, let me just close this window. I can close this. Make sure when you have a chance, look at important information, test number 1, the lecture folder, because those are things that you will not have to answer. All right. We're talking about ionic compounds. Everybody thumbs up, see my whiteboard? And this is material that will be on test number 2, which is coming up in a couple of weeks, not that long. Summer things are going to start accelerating pretty quickly, but it's something I've done many times before and students do well. All right, all molecules have a net zero charge. Therefore, we were doing this last week. All right. In case you can't read my printing, let me decode it, write the empirical formula. Empirical means the simplest formula of elements and how many atoms of those elements in a compound with the following ions. And the important thing to remember is all molecules have a net zero charge. And if we look at the first one, A, sodium has a +1 charge. I've got it written there. And bromine has a -1 charge. That's what this means. And does that add up to 0? And the answer is yes. So the empirical formula for a molecule with sodium and bromine ions is NaBr. Now, you cannot change the charge, but you can change how many. And I'll let you try this one once I write it correctly. And calcium +2 and fluoride -1. What would be the empirical formula for that compound? Your turn. When you're done, give me a thumbs up. Oh no, is the thumbs up emoji done? Broken? Oh no, it's working. And I see somebody already has the right answer. Let's do it. All right, calcium is a +2 charge and fluoride is a -1. And this has to add up to 0. Does it? No. You can't change the charge. Students try to, but you can't. It's always wrong if you do. But you can change how many. And if I have 2 fluoride anions and 1 calcium, that does add up to 2. So the numbers in front, notice this is no number means 1 calcium and 2 fluoride. And that's how you do it. Okay. Now I showed you how to write ionic formulas. Someone just asked, when is the test? -3. I'm not sure what that means. So the test will be this Thursday. We'll start around 9:45, 10 o'clock. And did I say test 3? I should have meant test 1. Once in a while, Dr. White even makes a mistake. We haven't done test 2 yet even. All right. Now, I've shown you how to write ionic formulas. We're not going to go into naming. On this slide, I'm going to turn the switch off. Remember, I do that. Click. Will this be on test or not? The metal ion is named as the element followed by the name of the non-metal ion. Script numbers are not mentioned. So the one we just did would be calcium fluoride. This will not be on a test or a final everywhere. You can look this up on the internet. That's why. Someone just asked when test 3 is. Look at the syllabus. The dates are there. It's on a Thursday in July. That's all I know right now. See me after class about that. All right. And metals form more than one positive ion. And there's ways for dealing that. You can have iron +2, and there's an iron, Fe is iron +3 ions. And those are called ferric and ferrous. And I won't go into that in this class. I know it, but I don't want to. Writing formulas from the names of a compound, the switch is totally off, and I'm not going to cover it. All right. I haven't done this in a long time. Switch is on. Click. Oops, click. You should know this. Hint, know this. Let's talk about polyatomic ions. Now, the word poly means many. And years ago, when I taught the other school, unfortunately, she passed away recently, sad, but very nice lady. Polly, I won't use her last name, was the dean of English at Elgin Community College. And at a get together, I got to meet her, know her, and she was a very nice lady with her partner. And when I met her, I said, "Oh, Polly, do you know your name means many in Greek? We use that in chemistry." And she gave me that look like, you know how many million times I've heard that? And she said that, and I apologize. But in Greek, the word poly means many. So polyatomic ions are ions made up of more than one atom or element, or more than one atom. I will never ask you on a test, what is a polyatomic ion? but is a group of atoms that have acquired electrical charge, which is shared among the atoms of that group. So polyatomic ion has a number of atoms together in a group that have a charge, electrical charge, like a plus or minus. Now, I will never ask about the naming of these. The names of the most end in the word ions, ATE. There are a couple on the next slide you need to know. Now, a couple you need to know. I won't ask you names, but you should be familiar with our NO3 minus is nitrate, NO2 minus is nitrite. Now, another one here, bicarbonate, is HC3O3 minus, and also the sulfate. So these are the ones you should be familiar with. I won't, where I have here, know these names, just know them, that they exist in their polyatomic ions. So what does that mean? Well, let's look at the following. Someone was nice enough to put down the dates for test 1, 2, 3, and 4. And thank you, Ismail. I hope I pronounced your name correctly. All right, let's look at the following. Right. Same question, write the empirical formula for a compound with the following ions. Let me check, you can see it. Thumbs up, people. Do you see it on your screen now? Write the empirical form. Thank you. All right. Let's do calcium plus 2 and nitrate minus 1, NO3. I'll do this one. Now, this is a plus 2 charge for the calcium, and the nitrate polyatomic ion is a minus 1. Does this add up to 0? And the answer is no. I can't change the charge, but I can change how many. If I have 2 nitrates, then this is what it would be. And how do you write that? 1 calcium, because the number there is 1. Now, when you have more than one polyatomic ion, how do you do that? Bracket, put the polyatomic ion, close bracket, then subscript, I need 2, so I'll do this. So that's how you write the empirical formula for calcium nitrate, 1 calcium cation, and 2 nitrate anions. Now, quick thing, sodium nitrite and nitrate I promise are preservatives in meat. And this is my own personal opinion. For many years, certain groups have said those compounds are hazardous to your health because they're in processed meats like bologna, salami, bacon. Bacon has a lot of that, or used to. And it's sometimes called pink salt because they color this compound pink because it looks just like sodium chloride, but it's not. And they say these chemicals cause serious medical problems. Do they? Don't know. But I cannot be honest with you. I've been eating salami, hot dogs, and bacon all my life, and look what it did to me. Oh, yeah, you better avoid those. No, seriously, I don't know if they do that, but I haven't had any health problems due to that, other things, but as with always, eat things in moderation, except for potato chips and French fries and pizza. All right, I'm going to let you have a try at it. Write the empirical formula for D, magnesium plus bicarbonate minus 1. Your turn. Remember, all molecules have a net zero charge. All. And remember, if you like, turn on your webcam so I can see real faces, not just names. How would you like this? No, I don't like it. All right, let's do this. How do you know what's the empirical formula for a molecule of magnesium plus 2 cations and bicarbonate minus 1 anion? So this is a plus 2. This is a minus 1. It has to add up to 0. It doesn't, but I can change how many, but never the charge. If I have 2, 2 times minus 1 is minus 2, plus 2 is 0. If you don't believe me, try it on your calculator. And therefore, we need, what's the coefficient here? No coefficient, 1. 1 magnesium, but now I need 2 bicarbonate. When you have more than 1 polyatomic ion, you have bracket, polyatomic ion, close bracket, then the number you need, subscript to the right, in this case 2. And that would be magnesium bicarbonate. And why don't you try another one? Sodium plus sulfate minus 2. What would be the empirical formula for that? When you're done, give me a thumbs up. See, a number of people are done. I'll give you another 8.7 seconds. Go. I'll give you another bonus 3 seconds. Time's up. All right. How do you do empirical formula? You look at the charge of the ions. This is a plus 1. And this is a minus 2. It has to add up to 0. It doesn't. I need a plus 2 to cancel out this to get to 0. So I do that. Now, what does this tell me? I have 2 sodium. That's how I show 2 sodium. And 1, when there's no number there, sulfate, SO4 minus 2. And that's how you would do it. By the way, this is sodium sulfate. How many of you have ever bought either electronics like a cell phone or other things, or what's another one? Optical equipment like binoculars or a telescope. I did those when I was young. Or they even have it in, if you buy, sheets of seaweed, dried seaweed, which Dr. White likes. You see those little packets and it says do not eat? Well, those sodium sulfate, the molecule I just showed you, Na2SO4. And that has the ability to absorb water and keep things dry. And that's why they put the packets in there. But I haven't looked up the MSDS sheet, but you know how to do that. It could be hazardous to your health, obviously. Now, one other one. And why don't you do this one? What would be the formula of a molecule with sodium plus and bicarb HCO3 minus 1? And when you're done, give me a thumbs up. All right, I see a bunch of thumbs coming up, so I'm going to jump in and do this. Also, it's getting near to our break time. And this is a +1 sodium, and this is a -1 bicarb, and it does add up to 0. So that tells me I have 1 sodium and 1 bicarb. And this is sodium bicarbonate. You know it as baking powder. And that's the structure, what's in the little red or yellow can. And that's how you do that. And with that, it's time for a 5-minute break. I'll see you at 9:55. I'm going to go stretch. I'll see you in 5. Time to get going again. All right. As I said, these are important polyatomic ions. Later in the semester, I'll talk about hydronium, H3O plus, and hydroxide, OH minus. And these are key polyatomic ions in our daily life. Ammonium hydroxide, you can have molecules with two different types of polyatomic ions. That's formed when you put ammonia in water. When you buy ammonia from the supermarket, you're really buying ammonium hydroxide. And writing formulas, we've done that. Remember, all molecules have a net zero charge, not only ionic, but covalent too. Oh no, if you look at where we are, it's time for part 2 of chapter 4. Now, thumbs up, people. Everybody see chapter 4, part 2 on your screen? Thank you. Whoa, now it's invisible. All right. So far, we've talked about ionic bonds. And remember, when atoms are joined together, they're held together by what we call chemical bonds. There's two types: ionic, which is caused by a transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. Now we're going to talk about covalent bonds, and those are where you hold atoms together in molecules where you don't have transfer electrons, you have sharing of pairs of electrons. Remember, pairs mean two. Let's go look. So the covalent bond involves, and this I won't ask you, similar identical ions. It can be atoms, it can be other things, but the most important thing is it involves sharing electrons. Now, a basic structural unit is called the molecule. Here's where I differ with some authors. I also call ionic compounds molecules. Now, what is a covalent bond? And you should know, covalent bond results from the sharing of pairs of electrons. Let's see if I have it written another way. Nope, I don't. You should know a covalent bond is the sharing pairs of electrons between two atoms. So what's the covalent bond? Sharing of pairs of electrons between two atoms. Now, how do we show this? By using Lewis structures for molecules and polyatomic ions. Now, I don't have it on a slide, but I should mention Lewis structures for elements and Lewis structures for molecules are a little different. And for elements, which you'll know for test number 2, you have one dot on each side before you double up, and you never have more than 2 dots on a side. For elements, for molecules, you can't have more than 2 dots on one side of the chemical symbol for an element. But let's look at this. Now, a while ago, I talked about the Octet Rule. And the Octet Rule are molecule atoms want to gain lose or share electrons that have 8 valence electrons, which is shown in the Lewis structure. There's one exception for the octet rule, and that's hydrogen. Hydrogen's octet, if we know the nearest noble gas, let me do this, for hydrogen is helium. So hydrogen wants to, in this case, share enough electrons that it has 2. That's the one exception to the octet rule. So each hydrogen atom has 1 electron, also 1 valence electron. It's only got 1, that's the outermost. And the question is, how do you draw a structure? Well, hydrogen gas, which is a molecule, exists as H2. It's a very explosive gas. How many of you have seen the video of the airship, otherwise known as a blimp, the Hindenburg, and back in the 1930s when it arrived in I forgot what city in New Jersey, during a rainstorm, it blew up and caught fire, and a number of people were killed. And there are 2 theories why that happened. One, it was a lightning strike. The other, because it was a symbol of supremacy for the Nazis, German Nazis, and Hitler, there was sabotage and someone blew it up. Which is right? I don't know, but it did blow up. And you can see that unfortunate tragedy on YouTube. But hydrogen was the Lewis structure. Now, each hydrogen has 1 valence electron. And this hydrogen says to that one, hey, I've got an unpaired electron. You've got an unpaired electron. Let's share. And they do. And this is now a covalent bond, a chemical bond. And remember, only valence electrons are used in covalent bonds. Now, if we look at hydrogen, the molecule, and its Lewis structure, notice this hydrogen, how many valence electrons does it have? You count shared and unshared, and the answer is 2. If we look at the other hydrogen, how many valence electrons does that have, shared and unshared? And the answer is 2. Remember, they wanted octet, but for hydrogen, the octet is 2. So both are happy, and you have a stable molecule, even though it does burn. Dr. White has worked with hydrogen for certain organic reactions, and I've worked at it where we use about 5, 6, 8,000 pounds, which is a lot of hydrogen, and it can be very dangerous. Now, again, formation of octet and covalent molecules. Atoms share electrons to achieve, and you don't have to know this slide, terms I'll never ask this on a test, but you should understand it. Atoms share electrons to achieve octets for valence electrons. And the octet, and I have the number 2 here, and really this should be, oh, wrong color. And to get a full octet, which I happen to be S and P orbitals, 2s, 2p, or 3s, 3p, or so on. Now, when we talk about Lewis structure for molecules, and hold on, I have to do something change for this slide. When we talk about a Lewis structure, there are 2 types of valence electrons we show in Lewis structure for molecular compounds molecules. And the first one is the bonded electrons. And what are bonded electrons? I'll never ask on test what are bonded electrons, but I might ask you to circle them in a Lewis structure. And those are pairs of electrons, the valence electrons, that are shared between atoms in a covalent bond. Remember, covalent bond sharing pairs of electrons between atoms. Now there's another group of valence electrons you can see in a Lewis structure of compounds, and that is non-bonding. Non means not. So non-bonding electrons are pairs of electrons, and they're always valence electrons that are not involved in electron sharing, otherwise known as a covalent bond. So you have bonded electrons, non-bonding electrons. Bonded are involved in the chemical bond, they're being shared, and there are always pairs of them. And non-bonding electrons are the valence electrons that are not involved in sharing. Oh, look, it's Lewis structure practice time. Now, the question would be, draw the Lewis structure for the following. If we had A, B, C. Now, let me do A first, and that's chlorine gas, Cl2. Nasty stuff, but it's useful. I've worked with it. And each chlorine, you have to first find out how many valence electrons does chlorine have. And how do you do that? You go to your friendly neighborhood periodic table, and you look, chlorine, Cl, has 7 valence electrons. So I know chlorine has 7 valence electrons. Now, I'm going to show you the mindset, and then I'll do the final structure. Each chlorine has 7 valence electrons. Remember, for atoms, 1 on each side and double up. And same thing here. Those are my 2 chlorines. And this chlorine says to that one, I've got a single valence electron. You do, let's share. And they do. So they share. Let me do my dots nicer. And this would be the answer for chlorine gas, Cl2. This is the Lewis structure. Now, if we look at that, each chlorine atom should have an octet. And if we look at the first chlorine, it has 2, 4, 6, 8 octet. And the other one similarly has that. Now, what if I asked you circle the bonded electrons in the Lewis structure for chlorine gas, Cl2? How do you do that? Well, we come over here, and which electrons are being shared, paired, and that's what you would circle. Now, if I asked you circle, and again, if I ask you circle the non-bonding electrons, those are all the pairs of electrons that are not being involved in a chemical bond. For those I've asked earlier, if you're colorblind, red, green, or one other, let me know, but nobody said that, so I'm using color. And a test, I might ask, circle the bonded or non-bonded electrons 1 or 2 points in a Lewis structure. Now, I'm going to give you one to try before we move on to water. And that's, why don't you draw the Lewis structure for bromine gas? And I will tell you, this also has 7 valence electrons. Your turn. When you're done, I'm going to do a polling. I haven't done that in a while. And it looks like everybody's done, so I better get to work. Each bromine has 7 valence electrons, and it has 1 extra, and the same thing here, and it can share. And that's how you do it. Each bromine has 2 on each side, and between there are 2 of them. Notice this is your covalent or bonded electrons. I didn't ask you to do that, but now let's do water. And I'll do this one. Come down here. Now water is H2O. Now, first of all, you have to find out how many valence electrons hydrogen and oxygen have. How do you do that? You go to your friendly neighborhood periodic table and say, hydrogen, how many valence electrons? Look at the number on top. Red, it's 1. Oxygen, how many valence electrons? Look at the number on top, and that's 6. So now we know hydrogen has 1 valence electron, oxygen 6. Now, in a test, you don't have to write this down, but it helps to write things down. Now, each hydrogen has 1. Each oxygen has 6. Now, there are 2 hydrogens, and this hydrogen says to the oxygen, you have a single valence electron, I do, let's share. And they do. And the non-bonding electrons here, and this hydrogen says, I have 1, you have 1, let's share. And they do. And now this would be the Lewis structure for water. Now, I'm going to let you try this. Why don't you circle in your mind the bonded electrons in water? Give you another 6.7 seconds. 6.2, 6.4, time's up. And what are non-bonded electrons? Those are electrons being shared. And that would be these two. And the question is, how many covalent bonds in water? And the answer is 2 covalent bonds. And then on oxygen, the non-bonded electrons are these. And we'll learn later on, those non-bonded electrons in oxygen play a very important role in our daily life. So the next time you see someone drinking water, hold on, you can tell your friend, neighbor, or loved one, you know, the water you just drank, that has 2 covalent bonds between the hydrogen and oxygen. People don't like hearing chemistry when they're drinking water or anything else. You lose friends quick. Don't. All right, let's do ammonia, NH3. And when I say let's do it, it's your turn. Draw the Lewis structure for ammonia. Now let's go to my whiteboard. This slide's, it's not my whiteboard. There's my whiteboard. Here's ammonia. This is ammonia. And first thing you have to do is find out how many valence electrons does nitrogen and hydrogen have. So I'll put up the periodic table. And the first thing you need to do is find out how many hydrogens or how many valence electrons does hydrogen and nitrogen have in ammonia? Time's up. Hydrogen, 1 valence electron. Remember the number above is the number of valence electrons. Nitrogen N, Roman numeral V, which is 5, has 5 valence electrons. So this has 5 valence electrons. This has 1. Now I will tell you, this molecule, nitrogen, is surrounded by the 3 hydrogens. Nitrogen is surrounded by the 3 hydrogens. Your turn. Draw the Lewis structure for ammonia. And when you're done, give me a thumbs up. I see a number of people are giving me thumbs up. Oh, let's do the polling too. Give you all some more time to finish. Remember the octet rule, and a hydrogen's octet is 2. The one exception to the octet rule. All right, let's get going. Now, nitrogen has 5 valence electrons. And organic chemists like to put the pair of electrons in nitrogen on top. Now, each hydrogen has 1 valence electron. And each hydrogen says to nitrogen, oh, I've got a single valence electron. You do, let's share. And they do. And notice I have 3 hydrogens, 1 nitrogen. Why don't you circle first the bonded electrons in ammonia? Time's up. This is 1, this is 2, this is 3. And then the last pair on top, these are the non-bonded. Now, let's take a look at ammonia. And this is another important thing you should do. If we look at nitrogen, how many valence electrons does it have? Shared and unshared. And the answer is, if I can get it right, 2, 4, 6, 8. It has 8 valence electrons, octet. So it's happy. Now, if we look at each nitrogen, I'll only do 1. How many valence electrons does it have? Shared and unshared. And the answer is 2 valence electrons. And remember, for hydrogen, the octet is 2. So everybody's happy. And ammonia is a stable molecule with the formula NH3, because that's the only way with nitrogen, hydrogen, you can get a molecule that everybody has this octet. Remember, hydrogen's octet is 2. Now, let me take a little side trip here and talk a little about ammonia. Now, ammonia is a very important molecule in our daily life. Well, you say that about everything. Well, it is. And around 1910, 2 German chemists found a way to make ammonia in chemical plants. In other words, in large scale, a lot. And you say, so what? Well, it turns out ammonia is so important, it changed our world. How did it do that? Well, by being able to make ammonia synthetically. Fancy word alert. Synthetic means to make. It's a fancy word for to make. How to make it, which means synthesize, make ammonia in a chemical plant. We now have a lot of cheap ammonia. So ammonia is used to make fertilizer. And now farmers, especially in the United States, had access to cheap fertilizer. Their fields yielded a lot more crops. In other words, there's more food, and that allowed the population of our planet Earth to increase, a lot more people. Now, that's one thing that ammonia was used for, because now it was cheap. We could make it in chemical plants throughout the world. And oh, by the way, those 2 chemists were Haber and Bosch, and it's called the Haber-Bosch method for making ammonia. Well, there's always so good, but sometimes there's not so good. Well, it turns out by having inexpensive, cheap ammonia, people were able to make inexpensive, cheap gunpowder and explosives. Well, now the militaries of the planet, our Earth, had access to cheap bombs and bullets. And therefore, unfortunately, wars were longer, like World War I, II, and others, because we now had access to ammonia to make cheap explosives. So, by what the work did, Haber and Bosch, one, the population of our planet increased, meaning less people were dying from hunger because there's cheap food available, because the fertilizer was available, and two, people were dying from longer wars. So what do you say? But that's real life. Molecules that have changed our world. All right, we talked about polyatomic ions, and these are ions which you have a covalent bond and an ionic bond. And the ions form covalent bonds between the atoms in the polyatomic ion. And let's just do one, and I'll do this one, and let's not do this one for now. I'll do another one later on. But how do you draw the Lewis structure for sodium hydroxide? Now, it's very important to listen closely. All let's get the periodic. All alkali metals and alkaline earth metals always form ions. Remember, hydrogen is not an alkali metal. All alkali metals, lithium, sodium, potassium, always form an ion. Same thing with alkaline earth metals, magnesium and calcium. Those two and a lot of the other metals, but for this class, you should just know those two alkali metals, alkaline earth metals, never, ever form a covalent bond. For years now, I've asked other colleagues of mine, chemists, do you know an example where what I'm saying is not true? And the answer is no. So if we go back, first of all, you have to know what ion does sodium form. Remember, we figured that out. What's the nearest noble gas? And that's 10. So it wants to have 10 electrons, but 11 protons, which means sodium forms a +1 ion. So immediately I can write for the Lewis structure Na+. Now, oxygen has 6 valence electrons. Hydrogen has 1 valence electron. We did that for water, so I don't have to take you to the periodic table. If I have an oxygen, has 6, hydrogen has 1, so it says, let's share. And if you look at this, we can now say hydrogen has its octet. But if we look at oxygen, it doesn't have its octet. What's wrong? Well, where did the electron that came from sodium go? And the answer is it went to the oxygen here. And so sodium hydroxide is this. The 7th, and the 8th one comes from the sodium. And because now it has a negative charge, I'll put it in brackets to show the Lewis structure. And this is how you do sodium hydroxide. Between the oxygen and hydrogen is a covalent bond. Between the sodium and hydroxide is an ionic bond. And they're both. And many things in our life have this. They're not purely ionic or purely covalent. Time for Dr. White to scare you people. How many of you washed your hands in the last 24 hours? I hope all of you, you don't have to do a thumbs up. I hope all of you did. Whether you use a bar soap, bar, or the liquid, I'm doing the pump, both of them, the key molecule in soap, which I'll teach you later in the semester, has both a covalent and ionic bonds. And that's what soap is. But because of that, it works quite well. And if you notice my hands, yep, they're still clean. My pen's clean, so I don't get them dirty from that. That was an awful joke. But next time you use soap, think about it. That molecule has covalent and ionic bonds in it. By the way, soap is a molecule, and that's chemistry, and how I'll teach you later on in the semester. How do you get your hands or whatever clean when you wash them? That's organic chemistry, which I'll teach you. All right, let's move on. Did I tell you who's the greatest of all chemists? It's Mother Nature. She's one of the greatest. And in our life, if there was only one pair of electrons being shared between atoms, we wouldn't have a lot of the molecules in our daily life. Well, it turns out Mother Nature and also chemists have different types of covalent bonds. And let's talk about the different types. If I had a dial that I could only turn up to 10, like on an amplifier, and I'm stealing this from Spinal Tap movie, I've just turned that dial up to 20. How much you should know this. And there are three types of covalent bonds. The first type is a single bond. And a single bond is a bond in which two atoms share one pair of electrons. Single bond. Next one, by the way, if you know baseball, when you go to first base, what do we call that? A single. And single bond, one pair, like first base, first one pair of electrons. The next type of covalent chemical bond, double bond. And a double bond is a bond which involves a bond between two atoms where you have two pairs of electrons. So single bond, one pair of electrons being shared between two atoms, double bond, two pairs of electrons being shared between two atoms. And notice, hint, know this. And finally, the third one is a triple bond. And a triple bond is three pairs of electrons being shared between two atoms. So we have a single bond, one pair of electrons being shared, double bond, two pairs of electrons being shared, and finally, triple bond, three pairs of electrons being shared. I should tell you, a double bond in a certain molecule we call fats and oils is important to make what's known as cis and trans. How many of you heard that trans fats are bad for you and cis trans are more healthy? And that's because of a double bond and how it looks. A double bond affects how my food is safe. The answer is yes. All right, let's review that. Instant table. First type, single bond. And involves one pair of electrons. Next one, double bond. That involves two pairs of electrons. Remember, pair means two. So how many electrons total in a single bond? Two. How many electrons in a double? 2 times 2, 4. But let's talk about pairs of electrons. And the final one, triple. A triple bond involves 3 pairs of electrons. So everybody, all together now with Dr. White, the first type of covalent bond, what is it? Single bond. How many pairs of electrons does it involve? 1 pair. Second type of covalent bond, double bond. How many pairs of electrons does that involve? 2 pairs. And the last type, triple bond, and it involves 3 pairs. So single bond, double bond, triple bond. Single bond, 1 pair of electrons, double bond, 2 pair, triple bond, 3 pair. And it's Lewis practice time for molecules with multiple bonds. Let's look at nitrogen, and I'll go over to my whiteboard. And nitrogen gas, which you're breathing in the air, about 80% of the air you're breathing is N2 nitrogen. Draw the Lewis structure. For nitrogen, I'll do this one, then I'll let you try one, because I like to share. Now, nitrogen, first of all, we have to draw the Lewis structure of a molecule, know how many valence electrons does it have. How do we do that? We go over to the periodic table. If we look, nitrogen has, oh, look, on top, V, which is also number 5 in red. Also, the other color, I wrote them in red so you could see them better. So nitrogen has 5 valence electrons. Well, it has 2 nitrogens. Each nitrogen is like this. And this nitrogen says, hey, I have 3 single valence electrons now, and you have 3. Let's share. And they do. Now, the non-bonding electrons are still there, and there's 3 pairs. And what kind of bond is this? A triple bond. And therefore, if we look at each of the nitrogen, I'll only do one, does it have its octet? Remember, all atoms, whether they gain, lose, or share electrons, wind up with an octet, except hydrogen's octet is 2. But here, we notice shared and non-shared. How many? 2, 4, 6, 8. And this nitrogen has its octet shared, and same thing if you do the same thing here. So it has its octet, and nitrogen gas N2 is a nice stable molecule. And the next time, that's not what I want to do. The next time you see somebody breathing, and you can walk up to them and say, you know, you just inhaled nitrogen, and that has a triple bond, 3 pair of electrons being shared, triple bond. People don't like hearing chemistry while they're breathing. Well, maybe except in my class. Oh, that was bad humor. Sorry. All right, time for you to try one. draw the Lewis structure, oops, for oxygen gas. Now, first of all, you have to find out how many valence electrons does an oxygen atom have. If we look over at the periodic table, hopefully you found out oxygen, O, look at top, VI, which is also in Roman numeral 4, 6 valence electrons. And being the super nice person I am, I'm going to let you have some fun. Draw the Lewis structure for oxygen gas. That's what's keeping you alive right now, one of the things. Also, think about what type of covalent bond are between the oxygen atoms. Then I'll show you, but have some fun on your own first. And don't forget my office hours site are from 5 to 6 because the Stanley Cup finals. Yes, I'm a hockey fan. I'm pulling for the Canadians. Don't ask me why. It's just, I'm pulling for the Canadians. I like to see the cup go back to Canada. It hasn't been there for a long, long time. Cup meaning Stanley Cup. All right, let me get to work. Oxygen. It has 6 valence electrons. There are 2 of them. Now, you don't have to write like I'm doing, but I'm showing you the way to think about it. Oxygen has, oh, I have 2 unpaired, you have 2. Let's share. 2 unpaired electrons, 2 pairs, and then the non-bonding electrons are still present in oxygen. Now, if we look, what kind of covalent bond is between the oxygen atoms and oxygen gas? O2. And the answer is 2 pair, which is a double bond. Remember, 1 pair is a single bond, 2 pair double bond, 3 pair triple bond. And that's how you do it. And the next time you see somebody breathing, you can tell them, you know, you're inhaling oxygen. That's a molecule with a double bond in the oxygen molecule. They don't like hearing that. With that, it's time for a 5-minute break. I'll see you in 5 minutes at 10:50. I can go stretch again. time to get going. And on a personal note, if you saw what I was doing, if you aren't following the following people on Twitter, you should be. And let me show you a few people. If you're not following Paul Krugman, I have for many years. He's a Nobel laureate and he's really good. You should follow his stuff on Twitter. Another person who's really good is Greg Sargent on Twitter. And I read him every morning or a couple times during the day. Another one from, I think it's Mother Jones. Yep, I'm right. David Korn has a lot of good stuff. And let's do one more, Jennifer Rubin from the Washington Times. She has a lot of good stuff. And that's my personal thing. All right, we're talking about multiple bonds, and we're doing practice time. And I'm going to let you try the next one. Hcn Hydrogen Cyanide is a very dangerous poison, but at the same time, why don't you, what's the Lewis structure for hydrogen cyanide? And let me go to the whiteboard because I'll help you out. Draw the Lewis structure. Hydrogen has 1 valence electron. Carbon has 4 valence electrons. And nitrogen has 5 valence electrons. I will tell you in this molecule, carbon is in the center because that's the only way you can make it work. And have fun. Remember the octet rule, and the exception, hydrogen's octet is what, 2? And when you're done, give me a thumbs up. Oh, I see one person done. Anybody else? Oh no, the thumbs up thing is broken. Or how many people want me to go ahead and do this? Give me a thumbs up. All right, let's do this. Now, each hydrogen has 1 valence electron. Well, there's only 1. Carbon has 4, and nitrogen has 5. And the hydrogen says to the carbon, let's share. I have 1, you do. And the carbon says, okay. And the carbon says to the nitrogen, I have 1, 2, 3, because this one's spoken for. You have 1, 2, 3, let's share. And nitrogen says, okay. Each of them have 3 single electrons, so that forms 3 pairs. The nitrogen still has its non-bonding electrons there. And this would be the chemical formula for hydrogen cyanide. Notice you have a single bond, one pair of electron, and a triple bond, three pairs of electron. So in this molecule, HCN, hydrogen cyanide, there's both a single bond and a triple bond. And if we look at carbon, notice paired shared electrons and non-shared. There's no non-bonding. 2, 4, 6, 8. It has an octet. Hydrogen has a octet of 2, and nitrogen also has 8 valence electrons, shared and non-shared. And up here, we have non-bonding electrons. Wow, there's a lot going on in that molecule. Now, on that page, and I'll do this one, let's do the last one, carbon dioxide. How many of you are familiar with the products such as in a can or a bottle, the non-alcoholic products you can buy that has these little bubbles in it? When you open up, you can see it. And we call that pop. Or if you buy beer or champagne, it has bubbles in it. And those bubbles are carbon dioxide. And when you burp, nope, I'm not going to burp for you. Most of your burp, or a good part of it, is carbon dioxide, CO2. Have you ever seen the frozen dry ice? That's carbon dioxide also. So what's the Lewis structure for carbon dioxide? Carbon has 4 valence electrons. Oops, getting ahead of myself. Carbon has 4 valence electrons, and oxygen has 6 valence electrons. Now, a carbon has 4 unpaired electrons. Each oxygen has 2 unpaired electrons. And this oxygen says to the carbon, hey, I have 2 unpaired electrons. You have 2, let's share. And they do. And this oxygen says to the carbon, you have 2 unpaired electrons, I do, let's share. And they do. And this is the Lewis structure for CO2, carbon dioxide. What type of chemical bond, covalent chemical bond, is between the carbon and each oxygen? It's a double bond. And therefore, each oxygen has a double bond to carbon. The carbon has 2 double bonds, 1 to each oxygen. So there are 2 double bonds in that molecule. And if we just look at this oxygen, notice it's got its octet, 2, 4, 6, 8. So does the carbon, so does the other oxygen in CO2. So next time you see someone drinking pop or beer or champagne or sparkling wine too, you can say, you know, the bubbles in there is carbon dioxide, and it has not 1, but 2 double bonds. Don't do that. People don't want to hear chemistry when they're drinking pop, champagne, beer, or sparkling wine. No. Now, this is a molecular model. If we had this for methane, methane is CH4 and carbon in the middle, and each end of the rod, think of a hydrogen. And notice this is not flat on a piece of paper. It's in 3 dimensions. This is called a tetrahedron, the shape of this. And this is the shape of the natural gas you use in your daily life. Now, listen carefully. Click. Do you everybody see that? Click. I've turned the switch. Will this be on a test for the next couple of slides to the off position? It's something you should know about, but I won't put on test or final. Now, molecules and ions too exist in 3 dimensions. They have shapes. And what determines the shape? It's called the Vesper Theory. Valence, I always forget what Vesper, something electron pair, valence shell electron pair repulsion. And valence, this Vesper theories, molecules exist in 3 dimensions and have shapes. And those shapes are important in understanding how molecules act, especially in our bodies and with certain drugs. Importantly, the shape of certain molecules and other factors play an important role how COVID-19 vaccine works and many other things in our daily life, like our hormones. Now, Vesper, I was right, valence electron pair repulsion should be, and shapes of molecules, again, switches off, are based on minimizing repulsions of the electrons of an atom in a molecule. So if we look at methane, otherwise known as natural gas, stuff you use in, if you have a gas oven and range, if you have, which most of us do in Northern Illinois, a gas water heater and also a gas furnace, you're burning methane. And the Lewis structure for methane is this: 4 hydrogens around carbon. Now, this doesn't show you what it looks like in 3 dimensions, which we call stereochemistry. Or is this, yes. How something looks in 3D. If I can spell. Three dimensions. Now, what's the factor? Electrons have a negative charge, and these electrons and these 2 bonds want to be as far apart as possible. Same thing all the way around. They want you stay away from me. Remember, opposites attract, but the same charge repels. Now it's time for Dr. White to ask a question, which I think, how many of you have ever played with bar magnets? They have a north and south end. If you put the magnets together, if they're opposite charge, they go like this. If they're the same charge, they repel. Opposites attract, the same repel. So electrons, which have a negative charge, want to be as far apart as possible. So how do they do that? Instead of being flat, they adopt different shapes. This is a methane, each line bar here, think of a pair of electrons, and this is a shape that makes them farthest apart. Remember, click, this won't be on a test, but still something you should know about. Now, based on the number of pairs of electrons of atoms, different molecules take different geometry, how they look in 3 dimensions. And some key ones, methane, again, switches off, is called tetrahedral. Ammonia is trigonal pyramid, and both the bonded and non-bonding electrons play a role. Same thing with water, is bent. And where do we get this? If we look at, this is from Wikipedia, when you have one lone pair plus 3 pair, it's going to take a trigonal planar, which looks like this. For methane, it will look like this, where it has 1 pair, lone pair, and 3 pairs. Methane, here is the non-bonding electrons, that's what the E is. It's, if you forget about the actual shape, where the atoms are, this is the structure of methane. Now, water has 2 non-bonding pairs of electrons. If A is oxygen, X is hydrogen, we have the non-bonding. It's still tetrahedral, but it looks bent. Ooh, this is cool. I forgot about that. And here, as you saw, the molecule I just showed you. Is this neat or is that neat? And for other things which we're not going to cover, there are other shapes that exist. These mainly 5, 6, and 7, and 8 are for inorganic molecules, but all the organic, remember Dr. White's, are 2, 3, and 4. And by the way, linear, something like this would be acetylene, which is an important gas. But anyways, that's the Vesper theory. Molecules have shapes, and that's due to the fact that the electrons want to be as far apart as they can in a molecule, and that's why they adopt these different shapes. Now, this is something we'll talk about, but I won't ask on a test. What is it? That's called electronegativity. And electronegativity switches still off, but it's an important concept, is the ability of an atom to attract electrons to itself. And the electronegativity of an element increases as you move from left to right in the periodic table, as you move from bottom to top. So let's take a look at the periodic table. Again, switches off. When you go from left to right, atoms of elements are more electronegative. When you go from bottom to top, they're more electronegative. So fluorine, and you, of the elements that are not the noble gases, is the most electronegative atom on the periodic table. And oxygen's pretty close to that. And some of the halogens are also very electronegative. And nitrogen is more electronegative than carbon, and so on. So what does this mean? And things like hydrogen, lithium, sodium, potassium are very low electronegative. Now, what's this electronegative? Well, think about if you're out in a rainstorm with your older sister. Shh, don't tell her I'm telling you this story. And you only have one umbrella, and you're sharing with the other person right here. But if you're bigger and stronger, you're sharing the umbrella more over you and less on the person who's weaker, because the bigger, stronger person can hold more of the umbrella over that person. Well, atoms are the same way when they're sharing electrons. So what does that mean? Well, if I'm sharing an electron pair or 3 electron pairs, I'm pulling them closer to me because I'm big and strong. And that affects the type of covalent bonds. Now, when there's equal sharing, like in nitrogen, we call that a nonpolar covalent bond. Switch is still off, but it's going to be turned on pretty soon. Now, when they're not, you have what's called a polar covalent bond. There's slight charge differences. Polar covalent, a covalent bond between different atoms of different electronegativities, like sharing the umbrella, but I'm bigger than you, I'm going to share it more over me. Don't tell my sister I'm telling that story. She was older, so I got wet in that rainstorm. Now, what happens is there's a slight change in the charge, even though it's sharing, and the charge is only partial. It's not a true ionic, since there's some sharing electrons. And we indicate this by the use of the Greek letter, the lowercase delta, and with the charge that exists. Now, this is delta capital. This means difference in chemistry. This is lowercase delta. This means little difference or slight difference. Between atoms. What does this mean? Now, water is H2O, and water exists like this. And I'm using a line now to show pairs of electrons. Organic chemists do that. Now, let's look at the difference between electronegativity of oxygen and hydrogen. And by the way, at this point, click. Will this be on a test? Yes. So you should know this. Hold on, let me get everybody's attention. You should know this. If we look at the periodic table, hydrogen is all the way on the right, left here. Oxygen's way over here on the right. So oxygen is much, much more electronegative. Remember, as you go from left to right, you get more electronegative elements. And it's when you go from the bottom to the top also. But in this case, oxygen being all the way over here on the right is more electronegative than a little hydrogen all the way over here on the left. So what does that mean? Well, here they're sharing a pair of electrons, but the oxygen says, I'm bigger than you, I'm going to hold them closer to me. So the hydrogen has a slight positive charge and a negative charge on oxygen. And the same thing happens with this hydrogen. So in reality, there's a slight, this is called a dipole, right here, di-2-pole polarities between oxygen, hydrogen, and water. Remember, this is water, H2O, water. Now, if I have another water molecule, same thing happens. Because of the difference in electronegativities, there's a slight charge difference. Now, the following, I better. Yep, 4 of them. Know this, when that happens, whenever you have charges, opposites attract. And notice this oxygen has a negative charge. This hydrogen, the other molecule, has a positive charge. So there's a very slight attraction. Between the water molecules. And this has a special name. And this special name, I'll even do it in blue, is called a hydrogen bond. It's not a true chemical bond, but it's a very weak attractive force. And we call that the hydrogen bond. And molecules with oxygen, nitrogen, or fluorine can attract each other. Each one has to have a hydrogen on it in what we call the hydrogen bonding or hydrogen bond. Now, how important is this very tiny little force between water molecules? Huge, really huge. How huge? Well, let me show you. Everybody see my water bottle? Hopefully you do. It's water inside. And right now in my office, our classroom, COD North, yes, I live north of the main campus, at room temperature, what is this? It's a liquid. Now, if you look at molecules that have similar molecular weight, which I'll teach you what that means, how much a molecule, they're all gases. Water is a liquid at room temperature, not a gas. What's causing it to be a liquid? Hydrogen bonding. Those tiny little forces. Can everybody see the water molecules in here? I can mentally see them. They're all being held together by that weak attraction. And think about it, on our planet, what if water was a gas now, not a liquid? Well, you wouldn't see it in this bottle. We wouldn't have oceans. Our blood wouldn't be like this. We wouldn't be like how we are, because all the important things that are in water would be a gas. How would we look? I have no idea. You can look and think about it in science fiction. Some people have come up with concepts of what if water was a gas, or if you're on the planet Jupiter, where it would be, but then you have ammonia as a liquid. But anyways, we have life as it exists today because of the hydrogen bond. Bet you didn't think about chemistry, that tiny little force between the oxygen and hydrogen and water, the hydrogen bond affects how life evolved on our planet. Interesting, huh? Yeah. And these form what we call polar molecules. And water, ammonia is another molecule that can hydrogen bond too. If I look at the slide, I don't know if you can see over here. Let me do this. If you look at the very lower left-hand corner, I'm on page 20 of 20 slides or pages. And you know what that means? It's new chapter time. It's time to get into some new stuff. And this is going to be really exciting, really juicy. What's this new stuff? Well, it turns out the way the book was written, Chapter 5 has some stuff I want to teach now, and other stuff I'm going to wait until later. So I split it up, and we'll do part of Chapter 5 now and come back and do the other parts later, because it makes more sense. In other words, it helps you learn chemistry better and do better on tests, which is a good thing. And let me open it up. Hold on while I close something down. All right, thumbs up, people. Everybody see Chapter 5, Chemical Accounting. By the way, my mother was an accountant. All right, thank you. All right, now, when we talk about chemistry, the fun part of chemistry is reacting things together. Dr. White likes to do that. I've been doing it for a long time. And we call this a chemical change, which occurs in a chemical reaction. And a chemical change, and I'll never ask you on this test, but you should be familiar because I use this term, is when an original substance is converted into new substance that has different composition. Because it's got different composition, it also most likely has new chemical and physical properties. And so this is a chemical change. Now, changes occurring during a chemical reaction. Same thing. The original substance is changed to a new substance with different physical and chemical properties. Uh-oh, the chemical properties thing came off there. Now, how do you know when there's a chemical change? Switches on. What's the evidence when you have a chemical reaction? You have a change in color. If something goes from blue to red or from clear to yellow, you know when you mix two things together, you have a chemical reaction. Also, when you form gas, when you mix two things together and you form gas, and you'll see what's gas? Bubbles. And when you see mix two things together, if you see a color change or if you see gas formation, bubbles, you've had a chemical reaction. Something has changed. The other one is when you form a solid. In chemistry, we have a fancy word for this, and that's called the precipitate. When a precipitate is formed, meaning a solid, when you mix two things together, you have had a chemical reaction occur. How many of you have ever seen those paperweights with the snowman inside? My sisters had those. And when you shook it up, did you see the little particles of snow inside the globe fall down? A chemist would say, oh, look at the precipitate in there. Whenever you form a solid, we call that a precipitate. By the way, we'll be using this stuff in tomorrow's lab. It's going to be fun. I guarantee it. And the last of the four things that's evidence when you mix things together, you have a chemical change, is a change in temperature. If I have two things I mix together and the mixture gets hot, temperature increases, we have a chemical change. If I mix two things together and it gets real cold, you've had a chemical change. How many of you are familiar with that pack you see you can buy that if you have a sprained wrist, ankle, or something like that, or you see it, athletes use it, and you need to put something cold on there to prevent it from swelling. You take this pack and you go crack and mix it up together, and all of a sudden that whole package or that kind of thing gets cold, like if it were ice in there, but there's no ice in there. What happened? Well, when you crack that, there's like a tube in there you break, it releases one chemical into another chemical. And when you mix it up, they react and you get a chemical reaction. And that chemical reaction makes the liquid in that package very cold because there's a temperature change. It gets way lower, colder. And next time you see one of those, let's see if I can find one. They're called cold packs. Oh, this one's freeze before used. Not what I was looking for. All right. Not that I get any kickback from who's ever selling this, but everybody see the cold pack on your screen right now? Let me make sure I got it set up. Everybody see that? Give me a thumbs up if you can see it. Where it says 4" by 5". Dr. White to Earth, Dr. White to Earth. Can you see it on your screen? Thumbs up, people. Uh-oh, thank you. For a second, I thought I had a strike of the thumbs up, people. And see right here where it says squeeze together here. What happens is in this cold pack, instant cold pack, there's water and a chemical called ammonium chloride. And what you do is there's a vial here that has the ammonium chloride. You break it and mix it, and this gets real cold. Why? Because there's a chemical reaction. So what's evidence for a chemical reaction? One, there's a change in color when you mix two things together. Two, there's formation of gas, which we call bubbles. And three, you see a solid form when you mix like two liquids together, and we call that solid a precipitate. And finally, four, when you see a temperature change, something gets cold or hot. Now, switch is on. I've just turned it up to 20. I will not ask what the definition is, but you should know chemical equation. It's a written statement that uses symbols and formulas instead of words to describe the change that occurs in a chemical reaction. And when you're, let me put up a chemical equation. Now here we have a chemical equation. For those of you who know, I'll be teaching you in this chapter what's balanced and unbalanced. This is unbalanced at this point. Now, chemical equation. I will never ask you the conventions, but there's certain ones. When you write a chemical equation, you have to put in the correct formulas for what the different atoms or molecules are in that chemical equation. And you need to use the correct formulas. Hydrogen gas is not H4. Oxygen gas is not H4, O2, O3 or O7. It's O2. And water is H2O. And this is how you do that. Now, the correct formula of the products are always written on the right, and the starting materials, also known as reactants, are on the left. Let me go through this. If we take our same chemical reaction, at the base of the arrow, these are called the reactants. Or if you only had one reactant, either reactant or reactants. Now, because Dr. White spent many decades in the chemical industry, and I'll do this at times, we call those the restarting material or materials. At the head of the arrow, for both academic and industrial chemists, we call this the product, or there's more than one, we call it the products. So if I were to ask you, what are the reactants in this chemical equation? And the answer is oxygen, H2, and O2, oxygen, hydrogen, H2. At the base of the arrow, you have the reactants, also known as the starting material. At the head of the arrow, you have the product or products. So in this case, water is a product. And when you have more than one, either element or compound, we use a plus sign. Think of that as and. So in this chemical reaction, the equation is hydrogen gas and oxygen gas make water. Again, base reactants, products at the head of an arrow. And that's what I have here. The reactants and products are separated by an arrow pointing always to the products I just showed you, and plus signs are used to separate different reactants or different products. And let me give you one to try. I talked about it earlier. This is not balanced. For those of you who know balance, why don't you, which are the products, which are the reactants of that chemical equation? Nitrogen plus hydrogen make ammonia. Time's up. Here's our arrow of our chemical equation for this chemical reaction. At the base of the arrow are the reactants. And I'll sometimes call them starting materials. At the head of the arrow are the products or products. So reactants for this reaction, nitrogen and hydrogen. Product for this reaction, because there's only one, and that's ammonia. Again, base of the arrow are always the reactants, head of the arrow are always the products. And that's the chemical equation for chemical reaction. And we'll be getting into that. And if I look at the clock, let me remind you, office hours, and I'll send out an email this afternoon, will be today from 5 to 6 p.m. And same thing for Wednesday. Don't forget tomorrow, I will be doing my world famous review for the next test, which in this case is test 1. And don't forget, the lab we did on Thursday is due tomorrow. Get your labs in. You don't want to lose easy points. They are. And like I said, tomorrow, I will do my world famous review. You don't want to miss it. And with that, I'm going to let you out a whole 2 minutes early. Don't tell anybody that. And with that, I'm going to say, gang gesund, be healthy. I will see you tomorrow. And Rain, thank you. Tomorrow's lab you'll really enjoy. And with that, gang gesund. Goodbye.